Hey everyone, welcome back. Today we're diving into a real classic, a problem from Irodov that looks pretty simple, but actually has this really cool twist involving, well, infinity. But don't worry, we're going to break it down and solve it together. Let's get started. Okay, so here's the problem. 1.158. We've got a 50-gram steel ball falling from 1 meter high onto a big, heavy slab. The question is, what's the total momentum it gives to that slab after numerous bounces? Now, numerous is a bit of a code word in physics. It basically means we have to consider an infinite number of bounces. And the last clue is this little Greek letter, eta. It's 1.25, and it tells us how much the ball's speed gets knocked down with every single hit. So right away, that's the big question, isn't it? How on earth do you add up the effect of an infinite number of bounces and get a real finite number? It sounds totally impossible, like the answer should just be infinity. But as you're about to see, there's a really elegant way to handle it.
Whenever you're faced with a complicated problem like this, the best strategy is always to start simple. So let's forget about all the other bounces for a minute. We're going to focus everything on just the very first impact. If we can get that right, it's going to give us the key to the entire problem.
Okay, first things first. We need to know how fast that ball is going right at the moment it hits the slab. And for that, we can use a trusty old friend, conservation of energy. As the ball falls, all of its potential energy, mgh, gets converted into kinetic energy, 1/2 mv squared. We set those equal, do a little algebra, and we find that the velocity is the square root of 2gh. We'll call this v1. This is the fastest it's ever going to move.
Now the problem asks about momentum, so let's just do a quick refresher. Momentum is just a measure of mass in motion. The formula is super simple, P equals m times v. The really important thing to remember, though, is that momentum has a direction. It's a vector, and that's going to be absolutely crucial in a second. To keep track of that direction, let's just decide that downward is the positive direction. So right before the ball hits, its velocity is a positive v1. Then it bounces. Two things happen. One, its direction flips, so the velocity becomes negative. And two, its speed gets reduced by that factor, eta. So the new velocity, as it rebounds upward, is negative v1 divided by eta.
And here's the key connection. Thanks to the law of conservation of momentum, any momentum that the ball loses has to go somewhere, right? Well, it gets transferred directly to the slab. It's a closed system. So if we want to know the momentum the slab gained, we just have to figure out the total change in the ball's momentum.
All right, we've totally dissected that first bounce. We know everything about it. Now we're ready for the really cool part. We're going to look at what happens next and the next because we're on the hunt for a pattern. There has to be some kind of predictable sequence here. And this table just lays it all out perfectly. Look at the first row. That's what we just figured out. Now after that bounce, the ball goes up and falls back down. It's going to hit the slab for a second time with the exact same speed it just rebounded with, v1 over eta. And look at the momentum it imparts. It's the exact same formula as before, just with a smaller starting velocity. You see the pattern? Every bounce is just like the last one, but with its speed reduced by another factor of eta.
And this quote just nails it. That's the secret to the whole problem. Each bounce is just a mini, scaled-down version of the one that came before it. This isn't an infinitely complex problem, it's an infinitely repeating problem. And that makes all the difference. So, we've found the pattern. The total momentum is just the sum of the momentum from bounce 1, plus bounce 2, plus bounce 3, and so on forever. This is it. This is where we finally face infinity head-on.
So if we take the momentum from each bounce and factor out the parts that are common to all of them, we end up with this expression right here. We've got this constant part out front, and then it's multiplied by this thing in the brackets. And that's an infinite series. It just keeps going forever.
And that looks terrifying, right? Your brain tells you, if you keep adding positive numbers together forever and ever, you have to get infinity. But you don't. The key is that these numbers are getting smaller and smaller really fast. And lucky for us, there is a perfect mathematical tool designed for exactly this situation.
And here is the hero of the day, the infinite geometric series formula. It's such a powerful idea. It says that if you have a sum of numbers where you get the next term by multiplying by the same ratio, r, over and over again, and as long as that ratio is less than 1, then that whole infinite sum is equal to a very simple fraction, the first term, a, divided by 1 minus the ratio. That's it. So let's use it. In our series, the first term, a, is just 1. And the common ratio r, the number we multiply by each time, is 1 over eta. Since eta is 1.25, our ratio's less than 1, so we're good to go. We plug those into the formula, do a tiny bit of algebra, and that whole scary infinite series just simplifies down to eta divided by eta minus 1. It's just so cool.
And just like that, we've done it. We've tamed infinity. We've replaced that endless addition problem with one simple little fraction. All the heavy lifting, all the conceptual work is over. Now we just have to put the pieces together and get our final number.
So here it is, our final equation for the total momentum. We take that constant term from before, and we multiply it by the sum of our series. We can combine a few terms, clean it up a little, and we get this beautiful, compact formula. It's just the mass times that initial impact velocity times the fraction eta plus 1 over eta minus 1.
Now for the big finale. We plug in the numbers we were given. Mass is 0.05 kilograms, g is 9.8, height is 1 meter, and eta is 1.25. You run those numbers through the formula we just built, and you get the answer. The total cumulative momentum imparted to the slab is about 2 kilogram meters per second. We did it! We got a real answer from an infinite process.
But look, the number itself isn't what's really important here. What's important is the toolkit you just added to your brain. We saw how to combine conservation laws, how to hunt for patterns, how to break a huge problem into small, manageable chunks, and most importantly, how to use a geometric series to solve a problem that deals with infinity. This is a strategy you can use all over the place in physics.
So I'll leave you with one final question to chew on. What would happen if the bounces were perfectly elastic? That means eta equals 1, and the ball never loses any energy. If you plug eta equals 1 into our final formula, you end up dividing by 0, and the whole thing breaks. So what does that mathematical breakdown tell you about the real-world physics of a ball that could bounce forever? It's a great little puzzle. Thanks for working through this one with me.